All right. How you guys doing? Doing okay? A lot of exams last week? Oh, today, I see. Gotcha. All right. Well, I need to apologize for last week for the exam. I had tried to make that second problem a little easier, and as I was kind of editing it, going through it, and I took out a portion to try to make it a little more straightforward, and I didn't think through it far enough because it also kind of ruined the rest of the problem. So that's what happened. I was trying to make it simpler, and I made it impossible or unreasonable to solve B or C or anything or that. So my apologies for that. I recognize that I only caught that with 20 minutes to spare, so some of you didn't even hear the update. Some of you might have been stuck on that problem a while. So I have begun grading the exams, but I haven't finished by any means. It's not likely that I'll finish by Thursday. But I will keep that in mind as I go through, especially if I see you were able to make a lot of progress trying the impossible and therefore didn't spend much time on the last question. I'll keep that. I'll be thinking about that as I grade. So my apologies for that. Any other questions or concerns on that? Okay, so a couple weeks ago we talked about wastewater for the first time. We had a few funny videos and stuff on what sewer systems are like and kind of that intro. We talked a little bit about the reason we treat our wastewater, talked a lot about the regulations side of things. Okay, we want our water not to catch on fire. We want our water not to kill all the fish. We want to be able to use it as a source for drinking water. Of course, with more treatment, but we want all of those things. So when we treat our water, we kind of keep lots of things in mind. And then if we can meet all of those objectives, then we typically will allow industries or municipalities to discharge wastewater, which, with particular treatment, we can maintain those intended uses. So with that, we do reuse, in a sense, a lot of our wastewater, right? We recirculate it through the environment, but in a sense, we will reuse a lot of it just because the hydrologic cycle cycles. There are some cases, Singapore is an interesting one, where almost all the wastewater is directly reused. So Singapore does not have much access to fresh water. It's a small island, very large city there. So if they need more fresh water, they either have to desalinate from the ocean, since I think they get a decent amount of rain, but it does not enough to collect and supply that large of a city, or they have to pipe it from their neighbors across some ocean. So it's not really economical to do much of that. So instead, what they'll do is they treat their wastewater to an exceptionally high treatment level, and basically use really high-tech treatments and get rather pure water as a result, and they recycle nearly all of their wastewater. Okay, so some of the technologies we talked about already for the drinking water side would be involved there because that's kind of cleaning it up all the way to that level. Probably reverse osmosis membranes in addition to a lot of other stuff. Okay, but bringing it back to wastewater treatment here, today we're going to talk about secondary treatment. Nowhere near enough to directly reuse, but this is the component that will allow us to get rid of a lot of that bacteria food that we don't want to send out into the rivers and waterways, right? Because if bacteria food in abundance is going out to the rivers and waterways, bacteria in the rivers and waterways and whatever other microorganisms will go wild, take up all the oxygen in the water, and it'll stink. It'll be bad, it'll be gross, it'll be stinky, and it'll clog up our rivers and waterways with biomass and depleting all the oxygen, killing all the stuff. So we don't want that. So the primary reason we do secondary treatment is to accommodate for BOD in particular. If we recall, that's biological oxygen demand. Could also call it biochemical or biodegradable oxygen demand. Basically, materials that organisms can eat and consume oxygen in doing so. So BOD removal is the primary goal of secondary treatment. Now, when we talk about secondary treatment, we can define this by drawing a little box around our treatment system where we would normally have a primary clarifier, and the effluent from the primary clarifier, the stuff that is sent away from the primary clarifier, is the influent for our secondary. It sounds kind of obvious for me to say it, but just make sure that if you see a problem, keep track of like where's the influent, where's the effluent, influent from what process, effluent from what process. That jargon is there, and sometimes will catch you in a problem. Okay, so the primary effluent comes in as our influent to our secondary system. Then the initial thing typically will be our bioreactor. That's going to be a spot where we aerate quite heavily, pumping lots of air. We'll have large blowers in a lot of these treatment plants that are just simply blowing air from the atmosphere into the water to create all these bubbles. Technically, you could supply direct oxygen, and that could work too, but that's kind of expensive. So we just typically just take air and blow air through the tanks. That'll mix them. So this will effectively be a well-mixed tank typically. So it will act like a CSTR. Of course, maybe we could design it in segments and then we have a series of them or something like that. But a generic tank will be a waste-activated sludge tank. A little more jargon there. Waste-activated sludge. Or WAS. Activated meaning we're activating it with oxygen, waste because it's waste, and sludge because it makes a slurry of microbes that can settle out into basically a sludge. So our activated sludge tank, that's where most of the biodegradation happens. So what we want here is a bunch of bacteria and a bunch of happy bacteria that are eating and reproducing and doing all the fun stuff in life, right? So they're just making tons and tons of bacteria, chowing down on as much food as they have available, and then we're sending them along the way. After that, the next part of secondary treatment is another clarifier. I say clarifier, this is the same thing as saying sedimentation basin. So we've already talked about what a sedimentation basin is. In wastewater, we just tend to call them clarifiers. It's going to have the same function. So when I talked about that primary clarifier, that's what I meant. It is a sedimentation basin. And it's very typical to see wastewater sedimentation basins as circular and called clarifiers. So same principle though, we're going to let all these bacteria then settle out of solution. And in general, we've grown up so much bacterial mass that that's not a terribly hard thing to do. And they will settle pretty easily. And we end up collecting quite a lot of sludge. Well, what do we do with that sludge? Well, here's one of the very important pieces of our waste system is we need to recycle some of that. In order to keep a happy, healthy, large amount of bacteria in our tank, we have to feed back some of these bacteria to them. Because if we just bring in fresh wastewater the whole time, of course there's bacteria in the wastewater, but not a huge mass of them. So we need to keep up a good starting composition, otherwise we're diluting them and there's not enough bacteria to really do our eating that we need. So we're going to send some bacteria back to recycle. So we will have a recycled activated sludge line, RAS. Send that basically to join the influent to the secondary system and recirculate some portion of our bacteria. Now we don't need to do all of them because then we would accumulate more and more bacteria and we'd kind of have too much. At some point the clarifier probably couldn't handle it. So we need to give it some amount but not everything. So the only other place to take them is through the WAS line, I guess the waste sludge line, and that's going to be a small flow that's just taking sludge away. And this would usually go to a digester or a sludge dewatering place and then shipping it off to a landfill. So basically, we're just going to get rid of the sludge in some way or another. Okay, that's not a lot of fluid, it's not a lot of liquid, it's just a lot of the solids from the bacteria. Hopefully, the rest of the bacteria, hopefully there's no, at least mass amounts of bacteria remaining in solution. Of course, there's going to be some floating around in there, but not like solid mass, not a measurable mass per se. And so then we have some, just the rest of the water leaving in the secondary effluent. And what we will talk about and what will become really important is we can assume that the amount of bacteria in that effluent is close to zero or close enough that we can control the mass balance of the bacteria without including what's going out in the secondary effluent, because the clarifier is supposed to capture it all. So that's the goal. So a couple notes here. We have a few terms that we're very familiar with. Q for flow rate, V for volume. X here is going to be a mass concentration for bacteria. And S is going to be a mass concentration of bacteria food. It's going to be the BOD. I've got more slides that will elaborate, but just to give you an impression here, we're going to end up with a system where we care about a couple of different things. The amount of food that's there, because that's our waste stuff that we need to get rid of, and the amount of bacteria there, because they are the ones eating the food. So we're going to end up with a system that has multiple mass balances if we care to deal with it that way, and a system that fortunately we can simplify and take the mass balance principles to take us to a more simplified approach mathematically and be able to handle our system that way. Okay, so we're going to use microbes. So here's the terminology a little bit again with a bit more context. So the waste activated sludge, or the activated sludge generally, that's the slurry of microbes. When we are aerating it or mixing it, that makes the whole system a CSTR functionally in the aeration basin. The clarifier is not aerated, and so usually we will assume that nothing important is happening in the clarifier in terms of the mass balance, in terms of the food being eaten. We just kind of ignore that. We might call the wastewater a high strength or low strength or weak or strong wastewater. Really, what that means is how much bacteria food is in there, how much BOD is in there. So a weak wastewater would be something like 60 milligrams per liter of biological oxygen demand per, so it's milligrams of oxygen demanded, or that could be demanded by biology, per liter. Just as a side note, the saturation for dissolved oxygen, we're going to talk more about this later. So the dissolved oxygen saturation turns out to be about, at room temperature, typically around 8 milligrams per liter. So if in every liter you're demanding like 50 or 100 milligrams of oxygen, then if you're not having really, really good exchange with the atmosphere, then you're going to go to zero oxygen really quickly. So if you discharge water out into a bayou that's already got some oxygen depletion from all the biological activity, and it's kind of slow and stagnant and hot, none of those factors help oxygen dissolve. Well, you discharge some wastewater there, you get a big problem really quickly, right? Because then the biological, all the biology around will consume the food, demand the oxygen, and you'll be left with water with very little to no oxygen left. Then all your fish and wildlife die, right? So it's not a good situation, and you also get really bad smelling products from the anaerobic bacteria processes that are going to happen. So the rotten egg smell kind of stuff. Okay, so that's the strength of wastewater. And that's kind of giving you that number to relate it to how much biological oxygen demand you could maybe handle with a liter of water if you're not mixing it with the atmosphere. You could handle more, let's say if you dump some BOD into a waterfall, plenty of mixing with oxygen. So if you had a very long perpetual waterfall or a river that has lots of rapids, it could actually handle more BOD than other systems because it's got that oxygen mixing. Okay, we'll save more discussion on that for later. We'll do a little bit of modeling on that after we handle wastewater. So the next topic or next category here we would say is volatile suspended solids. This term is referring to the X or the bacteria concentration that I said, right? The reason we're referring to bacteria in this manner is because it's very convenient to be able to weigh them as a mass, if possible. So normally, we can't take one bacteria and pluck it up and put it on a scale and weigh it. They're a little too small for that. We don't have scales that precise. So instead of doing that, we're going to filter a bunch of them, and we've got tons and tons of bacteria anyway. So we're going to filter them onto a plate or onto a little filter. Then we're going to dry that, and that dry mass is the total suspended solids. And then we're going to bake it. And not just bake it, we're going to put the oven on heat, on the self-clean, and it's going to go up to 500 Celsius and really blast anything that could volatilize away. And then we're going to weigh it again. So we weigh it dry, and then we weigh it extremely cooked, and then we figure out the difference, and we say that's how much could volatilize. Basically, what's left is ash, right? Anything that's ash, that's mineral, that could not escape. So it's not a direct measurement of the bacteria by any means, but it's a measurement of any particle that was there, and some of that particle could volatilize as CO2 or nitrogen or whatever else. So it's a pretty good estimation of how much organic material was there, stuff that will burn. Okay, so that's going to be the volatile suspended solids is whatever is left after the incineration. Excuse me, the difference between that, the volatile suspended solids is the difference between what you weighed dry and what you weighed just the ash remaining. So that remainder kind of indicates what was not biological. Or organic. Okay, so all told, this just gives us a way to get a mass concentration of bacteria, which is pretty handy, and a way to perform this measurement in the matter of a few hours, right? Take it, filter it, dry it, and then bake it. Okay, typically our targets for how well does this work? We're going to aim for 95 to 98% of BOD removed. So if we had a strength of 100 BOD per milliliter, now we're down to 2 to 5 range milligrams per liter BOD. So if our wastewater strength was 100 and we remove 95%, now we're at a level that even if we did put it in 1 liter of water and prevented that exchange for with air, it would probably not bring the total down to 0, even with that amount of biological activity. So that would be great. Now, as I said, we'll get more to all that later, but that's the typical. Now, if we recall, I talked about this a little bit already. We have some ratio of nutrients for the microbes: C for carbon, N for nitrogen, and P for phosphorus. It's kind of what biological material are made of. Usually we'll treat the secondary system as if carbon, to try to get rid of most of the carbon demand. So carbon would be kind of the limiting function here. But at some point, we've removed most of the carbon, and then we might have a lot of nitrogen left over, so that might tell us we need some different treatment tertiary treatment to get rid of more of the nitrogen. Or in some cases, I think I mentioned that tissue recycling plant example, they actually had a lot of carbon from this tissues, the fibrous materials from recycling paper, but almost no nitrogen or phosphorus. So in order to remove them, in the first place, they had to add fertilizer. Just like buckets of fertilizer to fertilize the bacteria to let them grow and remove the carbon in order to handle that, to tackle that. Okay, I also have a quick little video of a typical secondary treatment plant. Here I'll bring up just a moment. So what we see here is probably the influent. So water's coming in, and then this first step would likely be on the right. That would be the primary clarifier. I'm guessing here. I don't know this plant in particular, but that would allow as much as you can to settle as it's passing through that first chamber on the right. Sometimes you might also have an equalization basin that might be serving that function. Equalization basins help you keep your flow rate the same the whole time. If you have high flow rate, sometimes low flow rate other times. But I think this is a clarifier right there because it's overtopping along the edge there, meaning we're not collecting from the bottom. So it's overtopping, flowing into that channel, then heading from there into this activated sludge chamber next. And you see it's quite active with all the bubbles. We've got plenty of guardrails. You know, it might be obvious to you that you don't want to fall in there, but what might not be obvious is that if you did, you can't swim because all the bubbles are going to remove all your buoyancy. And so then you sink. And if you fell into a wastewater treatment plant like that, you have to walk until you find the ladder. And hopefully you get there. So if it wasn't obvious, be very careful if you're walking around an activated sludge chamber. It's also why you don't, if you're ever on a sinking boat, you probably want to swim away from it to avoid all the bubbles that will follow as it sinks. Buoyancy is helpful. Okay, so we've got a couple chambers here. You can see two chambers of this activated sludge. And so it's probably going to act like two CSTRs in series. We didn't really talk too much about sequencing reactors, but it's something that we could certainly do. I don't think I covered it with you guys, so we're not going to deal too much with it. Then once we're done with the activated sludge chambers, we're coming back here, and we see it's really nice and rich and brown with bacteria and a lot of scum layer on the top. And now we're going to let it sediment again. And you know, it feels a little weird that we wanted to make it dirtier, but what we're doing is making it more particulate, right? So after that sedimentation chamber that we just walked by, now this is probably, if I were to guess, where they would be dosing with chlorine or doing any other kind of disinfection step. And this is not this is a fairly compact plant. This is not a very large plant here. And then you see here, this is essentially our secondary effluent. Looks like that might just be where they're going to, they're essentially done. So I would guess this would be a small city or a large village type of plant, maybe 20 to 50,000 people or something like that. I would be surprised if it was much more than that. And you see here the water coming out actually looks a lot better, right? It looks a little bit more like river water, something that's much more reasonable than what was coming in. Still wouldn't want to drink that. Okay. All right, so the question for us becomes, how do we model the growth of the bacteria and the removal of the substrate, the food? This is our challenge in terms of engineering a system. How do we design it? Well, we need to know how are we going to, at what rate do the bacteria grow, and what does that depend on? Excuse me. So, a little bit more terminology, and we're going to cover some terminology so that we can use what's called the Monod equation. This is essentially a growth equation that defines our rate constant. Okay, so we've done rate constants for a while now this semester. We have some rate of change for our bacteria, and I'm going to say rate of growth for the bacteria. We could say the rate of change of x is going to be equal to some function that looks like k times x to the 1 power, right? We've seen that. We've seen things that look like that. But instead of k, I'm going to say this is now mu. So mu is essentially a rate constant. Okay? That's all I'm saying here. Given that, we can make a lot of sense to this and relate it to everything else we've been doing in the class so far, or almost everything. So, just like we had when we dealt with some of the flocculation stuff, we had some equation to give us the k for how fast particles are meeting each other. Now we have some mu, rate constant, for how fast are the bacteria going to grow. Okay? So, we define this as the maximum possible rate constant that we could find for bacteria, mu max, times the amount of food divided by the amount of food plus some other constant. Okay, so there's going to be several k's involved, and I'll try to be very clear, have them written here. This one at the denominator of that is the half velocity constant. We'll talk about that in a moment. So x, we've talked about. This is our microbe concentration. We're going to describe that as milligrams of that VSS term, volatile suspended solids. We have a way to cook the solids and see how much volatilized per liter. S is our bacteria food, and we're measuring that by how much oxygen the bacteria are going to demand. It's kind of a strange unit, but it makes a lot of sense. Very convenient. Mu is that specific growth rate coefficient. This is a first order. We see it's per time unit, usually per day. This is why I went ahead and put the x to the 1 power here, because I already knew it was going to be first order. That is specific to our particular condition that we have. Now we have mu m, which is or mu max, the maximum specific growth rate coefficient that this type of bacteria or this mixture of bacteria could ever achieve if we gave them as much food as they possibly wanted. Okay? This is just when they are super, super happy. We'll say at infinite food. So they have as much food as they could possibly handle and want, and then some. This is the rate at which they grow. Now, our particular condition, of course, might not be that, right? It might feel that way at first, but effectively, that's not going to be the case. So S then is our substrate concentration, the amount of food, milligrams BOD per liter. I repeated that now, so apologize for that. Need to revise that. Ks is the half velocity constant. This is just essentially saying the value at which the bacteria are halfway happy. They are consuming food based on, at a rate that is, excuse me, let me rephrase that. This is the amount of food where the bacteria have a growth rate constant that is half of their maximum. I'll show you that on a graph. It's not too important. It's just, You can think of it just as a constant. I'm just explaining it so you know where it's coming from. And if we look back at the equation, it's like the maximum possible times the amount of food divided by like 1.5, or the amount of food plus half of what would get them to happy, like fully happy. So this is the what that would look like if we plotted mu versus the substrate concentration. We would have some maximum. As we give the bacteria more and more food, we get closer and closer to the maximum. Okay, so we're going to say if they have no food, they start at 0. And eventually they get closer and closer and closer to that infinite happiness max food. All we have to do is find the half here, 1/2 of mu max, and then bring that over to here and say, okay, that's the amount of food where they're halfway happy. That's our KS. Now, you don't need to worry about this. I'm just explaining to you where it comes from, just kind of so you know. But this is kinetics that microbiologists will use quite often, and people digging into the nitty-gritties of wastewater treatment in the microbial sense. This stuff and all the different factors that would affect this kind of thing is perhaps interesting for them doing their research. Okay, so that's the uppercase Ks, the half velocity constant. It's like the bacteria growing at half the velocity, at that particular amount of food. So our current value of S could be anywhere along here, right? And then that would feed into our Monod equation for S. Okay, so that's kind of in practice. You'll be given a value for Ks, probably. I mean, I guess maybe we could solve for it, but typically you'll be given a value for S. You'll be given a value for Ks. We're finding mu, and we need to know mu max, or maybe you're given mu max and we need to find mu, something like that, right? So just different pieces that are typical for a system. Okay. I want to give you one other picture here about microbial growth so that you can kind of understand a little bit further about how microbes work and how we can expect them to act in reality. So if we take some microbes and put them in some nice warm environment with lots of food, let's say I put some good broth in here that has lots of microbe food, and heat it up to maybe body temperature, and I just let it grow and let it sit there. You've accidentally done this when you left food out and it got warm and stuff started growing on it, right? Hopefully not, but happens sometimes. And it'll smell like something's decaying or rotting or whatever. Something's growing, right? If we let bacteria grow and we give them enough oxygen and food, they're going to grow and grow and grow. But there is a limit, right? So if we just take a jar, for example, that we have like here, and we do it in a batch system, what we will find is at first there's some lag phase. We have some bacteria there, but there's not many. They're starting to replicate, but first they have to kind of figure out, oh, hey, there's food here. Oh, hey, the environment's good. Yeah, let's make babies, right? And bacteria are not quite that exciting. They're just, splitting. So it's, they're just doing their own thing. So, but they're going to multiply and then start accelerating. And this is why we have, if you ever think about like foodborne illnesses, if you go to a picnic, let's say Sunday afternoon church picnic or something like that, and there's like some stuff with eggs, which are nice and nutritious. Eggs sometimes have bacteria. Well, if you get it while it's fresh and early on, there's not much of a risk. But if you wait a few hours and maybe there's some contamination and it's a hot sunny day, well, suddenly you're at more and more risk for getting a foodborne illness if there was some sort of contamination, because now any bacteria that are there and happily growing in the nice media, well, now they're growing at an exponential rate. So this is the growth phase. They've now accelerated, And then depending on how much food there is, this would typically, like in just a jar of lots of food, that would probably take about 24 hours. So this is not a strict timeline. It really depends on the type of bacteria and everything. But we might imagine something like 24 hours later, we're hitting a point where we've grown to the maximum. It's full of bacteria to the point where we reach what's called a stationary phase, and now the rate at which they're growing is about equal to the rate at which they're dying, because bacteria don't live a whole long time. So they're also going to be dying, especially if it's a warm environment. There will be decay, things like that. So at this point, we have reached a steady state, at least temporarily, where we have they're still growing because there's still some food there, and when the microbes die, that becomes food for new microbes in a way, and they're also dying, and those rates have equaled. Now, eventually, we really run out of food or good enough food, so the growth rate gets pretty small, and the death rate dominates, and then we have a decay phase. So that's what would happen if you put a bunch of media in my bottle and left it in an incubator for a week. You'd end up having lots of bacteria, and then they're dying off. But way too many bacteria for my interest in consuming. So that's the bacteria. Along the same lines, we could also think about how the substrate is changing, right? And in fact, I actually mentioned that as I was talking about the relevance to the bacteria, right? I was like, well, now they ran out of food. So if we're interested in the substrate, we could look at the ds dt, right? The food is changing over time, and it's probably going to look something like this, right? The amount if we were to plot the food, I'll draw that a little better. So there's that inverse correlation in terms of the bacteria are growing quite happily up until there's not really enough food left over. So that kind of gives us a little perspective on how we might expect our systems to interact here. All right, so let's start with growth then. Our growth rate, we already talked about this Monod equation. That's giving us our rate constant. So we can define our rate as this is a growth reaction, right? Because a lot of the reactions we've done so far have been in decay. So now we have a positive instead of a minus. So our dx dt is mu x. And you think of the mu as a rate constant. Okay? So dx dt equals kx, in this case mu x, and we have a definition for the mu, or a formula for it. So Rg, the rate at which we're growing, is mu x. We could then put mu here, substitute it in, and say R of g is equal to x times mu max times s divided by ks plus s. Boom. There's our rate of growth. Now, we can put that rate equation into a mass balance, right? Could be a batch reactor, could be a CSTR. We can do with that just like we've done with our other reactions earlier in the class. Okay, so we're going to set that aside for a moment, and now I'll switch gears to think about how the substrate is changing and relate that in some sense to our growth rate. So substrate utilization rate, in order to get there, we want to find how much substrate is being used per bacteria we're making. So it's going to be a little bit not backwards, but a slight inversion here. So we're going to get this yield coefficient, meaning how many bacteria can we produce per hamburger we eat, kind of thing, right? And so we can define this yield coefficient as the milligrams VSS per milligrams BOD. I don't know why I didn't just put that here. So the milligrams of X per milligrams of S. Now, if we take X divided by S, those units would cancel. I'm not suggesting we should deal with this equation exactly in those terms. I'm just kind of showing you that's effectively what's happening, right? It's the mass we get per food we ate. So it's that ratio. So if that's y, then we can also define, and here I'm going to erase my k over here because the k's are coming back and forth, and we gotta account for that. We can define our yield coefficient as lowercase k is equal to mu max divided by the yield coefficient. Now, this lowercase k is the maximum specific substrate utilization rate. Okay, that's a lot of words to say. At the maximum capacity, if the bacteria are eating as fast as they can, here's this is the rate coefficient for that condition, and it's defined as mu max divided by that yield coefficient. Okay, so that's a little bit of a roundabout way of getting to our yield coefficient, and remember this is a different k than the uppercase ks, so not equal. So don't think about that right now. Okay, and this maximum specific substrate utilization rate has units of milligrams BOD per milligrams VSS per day. Because it is a rate constant or rate coefficient, it has the per day units. And so whenever we're dealing with the yield coefficient, we need that coefficient and we need that max constant, the mu max constant. So lots of constants coming into here. You'll have an equation sheet that's quite thorough. I'll make sure to post that pretty soon. And the task then is to make sure you kind of understand where the pieces are coming from and what their names are, what they mean, right? Okay, so going on from there, if we want to define the rate at which substrate is utilized, substrate utilization rate, so we'll say substrate utilization rate is RSU. Well, we can define that, given now that we have y, we can define that in terms of the growth rate. Because that y lets us convert between that yield is the y, lets us convert between the substrate and the growth. Okay, so the y is that connection. And I apologize, this is a little bit of a roundabout way of defining y in the first place, but ultimately that's what we're doing, is we're describing that distinction. Is we get some amount of bacteria produced given some amount of substrate. So we can get the substrate utilization if we know the y, and that's going to be the substrate utilization rate is going to be equal to the rate of growth divided by yield, and it's going to be the negative of that because we are consuming the substrate while we are growing the bacteria. Okay, so hopefully that makes some sense. We have Rg equals mu x. We then have R of the substrate utilization equal to negative Rg divided by y. Now the only thing remaining that we might need is the rate at which the bacteria are going to die. Okay, so we have another dx dt, this time a decay rate, so Rd for the death. So this will be kind of that death phase, or the rate that dominates during the death phase. And we can define this pretty simply. It's going to be a first order rate constant. If we have a lot of bacteria and a portion of them are dying every hour, then it's first order with respect to how many bacteria are there. So this is going to be a third k, this one with a d as a subscript. So Rd is equal to negative kd times x to the 1 power. It's a first order, right? So then this is pretty straightforwardly a coefficient of decay with a first order unit, which is per time, usually per day. Simple as that. Okay, so now we have two rates for the bacteria. We haven't done many systems where we're doing multiple rates for a given thing, but it's not too complicated to handle. We can do a mass balance, for example, with a growth and a death rate and solve for that. And we just need both of those components within the rate term, right? We've done multiple inputs before. We've probably done multiple outputs before in a mass balance. There's no reason we can't do multiple rates in a term. Okay, so putting these together then, we could get a net growth rate, which would simplify even further this process of setting up a mass balance, and say the net growth is going to be R prime G is the rate of growth plus the rate of death, right? We could say minus the rate of death, but the minus is already kind of caught up in there. So with that, we can then do something a little fancy. We can say, instead of just dealing with the rate of growth, what if we substitute the substrate utilization there and put that minus y times RSU? That's kind of coming from what we did a minute ago, saying RSU is equal to negative RG divided by y. If we rearrange that to here and then substitute that in, we end up with a term for the net growth rate in terms of the change of substrate and a death rate that's relatively straightforward. So that might be useful because we can just track what's happening to the substrate, and we know something about this constant, and we don't have to deal as much with the growth rate kinetics. So sometimes that'll be useful to rearrange it in that manner. We can actually cancel out some of the terms, the variables that we had to deal with. So we'll see some of that. Okay, so I want to take a look at this example. We have BOD consumption in a pond. We've got a bunch of characteristics for this pond, the different species and different items in here. And it says the shallow pond depicted here stays well mixed due to the wind and steady flow through of a small creek. And so what we're going to be asked for is to find essentially the amount of substrate leaving and the amount of bacteria leaving. So XF and SF. See that right here. So the question, I'll come back to all of this data for us to solve. I'll just note real quick, I'll read through these things and then I'll go through and read the actual problem. So we have a few typical parameters provided for, and we're told to use these ones. So for example, a typical value for K, this is the lowercase k with no subscript, that's the maximum specific growth rate yield coefficient, or what would we call it? Utilization rate coefficient. This ranges from 2 to 5, or 2 to 10, excuse me, and we have a default value that we're going to use as 5. So we've just got a table here. I'll probably give you the values directly. You might have to recognize what the names are, but I'm just giving you a quick overview of what the table is showing you. This mu max in per day is typically between 1 and 10. Default value is 3. The KS, it's the half velocity, half the food to make them happy. Typically somewhere between 25 and 100 milligrams BOD per liter, and our default is going to be 60. The yield coefficient is usually between 0.2 and 0.8, and we're going to use 0.6. And the KD, the death coefficient, is usually between 0.025 and 0.075. We'll use 0.06. Okay, so all these parameters, I'll put them back on the slides in a minute, or they'll be there. We got this pond. We're going to solve for the amount of substrate leaving and the amount of bacteria leaving after they've grown in the pond. So the pond itself is well mixed. So that's indicating to us that it's pretty much going to act like a CSTR. We do not have any recycling of our bacteria. As we'll see with this problem, when we don't have any recycling of bacteria, we can solve it directly with the mass balance like we're going to. which is maybe a little more complicated than using the formulas that we'll use for the recycle systems. But we'll get there. I just want to show you what it's like putting these pieces in together, putting the mass balances into a rate equation like we've done, but for this system. Okay, so it says if the microbes in the pond consume the inflowing biodegradable organic matter according to typical kinetics, that's those default values and all that, determine A, the BOD5 leaving the pond, that's the substrate leaving the pond, B, the biodegradable organic matter removal efficiency for the pond, so this would be, we're not given any equation for this, but it's not too hard to recognize, well, removal efficiency should be how much we removed, or I guess how much is, yeah, the removal, the portion removed times 100%, right? So this should be S naught minus S. So what we started with minus what we ended with, divided by what we started with, times 100%. And C, the concentration of volatile suspended solids leaving the pond, that's X. Okay, and I've got the first little bit there lined up, and I've got another slide where we can kind of put it all together. So I'll start you by kind of putting you in line with how they're starting and giving you a little bit of a framework to work. I'll put up some equations for us again. And this one is pretty involved, so I'm not going to give you like the remaining half hour to just try to spend all that time on it. I will walk with you through it, but I want to give you a chance to think about where to start and where you run into like a challenge in terms of, oh, how do I do that? Okay, so the solution says the pond can be modeled as a CSDR. We'll assume the stream has been flowing pretty steady, so we can expect it has reached a steady state after a long period. We're not given any information otherwise. And so first we want to set up a mass balance on the microbial mass using the pond as a control volume. Variables in the figure we can write, so using that and the variables we can write 0, so the accumulation rate is equal to what's coming in minus what's going out plus the reaction term. Right, so in that volume, R prime of G. Okay, so that'll be the first step. And what's interesting is you could start tackling, or you might think to yourself, we need to mass balance on the substrate. Right, part A is asking for substrate. And the counterintuitive thing here is it turns out to get substrate, it's easier to find, to do the mass balance on X because those two are linked. So I'm going to give you that tip up front and say, start here with a mass balance on X, and you'll see that we can solve for S. And later, once we have S, we can then do the reverse and do a mass balance on S to find X. Okay, so that's like the tricky part that you probably wouldn't have any reason to think about. So I'll take a couple minutes to start writing the pieces that, the equations and things you'll need, and maybe give you 10 or 15 minutes to work on this. Feel free to work with each other, ask me. Just use this time to kind of challenge yourself to approach the problem. Do you guys find this approach helpful to kind of work on it, me work on it a little, and give you time like this? right, so I'll take you through what I've done so far and see if we can get through part A, if not further, and might pick up the rest of it the next time. Okay, so a couple things to note. I went ahead and wrote up all the information we had. Some of it, of course, we didn't have right on the page until I wrote it. So some of the default values I pasted over. I reminded us that mu is, got the formula for that, mu max s divided by ks plus s, and that we can define r prime of g as the growth minus the decay, or the rate of growth plus the rate of decay. And we have equations for each of those, mu x for the growth and negative kdx for the decay. So with that, and with remembering that our x finals, since this thing is well mixed, should be the same thing as x in the lake, then we have xf equals x, and our equation that we're starting with actually becomes a lot simpler. Well, first of all, our x naught is 0. We don't have a whole lot of bacteria in the inflowing stream, so that goes to 0 and brings the first term to 0. So we have 0 equals 0 minus qx plus vx times, and I went ahead and took the v and the x out of the terms here, so it's v in that volume, the r prime of g, and the r prime of g had two terms. Each of them had x because they're both first order with respect to x. So I went ahead and just simplified a little bit here because we should have had the x here and the x here, but I took them out. Meaning I pulled them out, factored them out. So we have Vx times this mu max s divided by Ks plus s minus Kd, all in that term. And if we look at it right here, what we really just need to do is solve for s. And looking ahead, there's going to be some annoying algebra, but totally looks possible, especially because we can get rid of the x's altogether. Because we almost had a situation where we had two unknowns, right? X and s. We need both, and we don't know either, right? That's a conundrum. But given that we don't have any recycle, we actually have a shortcut here because these will cancel. Because we can add qx to both sides and cancel them, divide everything by q, that puts us into theta and gets rid of the v. So we have 1 equals theta times this mess. So from here, there's some algebra, right? And thankfully I have the final end target here in case I wander away the wrong way. But let's just go ahead and tackle this and see if we can solve for s here. So it should be 1 equals theta mu max s divided by ks plus s minus theta kd. I just went ahead and multiplied both things by theta, unfactored it, so to speak, so that then I can get the s terms by themselves. So I'll have 1 plus theta k, this is kd, excuse me, equals this theta mu max s divided by ks plus s. So I need to multiply that denominator by both sides. It's going to be a little factoring over here. So we'll get ks plus s times 1 plus theta k is equal to theta mu max times s. Okay, all of that is all right so far, and now we need to just cross multiply this stuff. All right, so we'll do the k's first, ks plus ks theta k plus s theta k, if I did that right, equals theta mu max times s. All right, now we just need to get all the s terms by themselves, and I'll go ahead and just subtract the s and s theta k from both sides. So we'll be left with, and I'm going to carve out a little space for myself here. keep it a little clear. So we're going to say Ks plus Ks theta is equal to theta mu max S minus S theta K. Did I drop the D again? The whole time, right? Sorry about that. And I dropped the KD altogether here also. Okay. All right. So then we can get, on the right side, we can factor out the S and have S times theta mu max minus 1 minus theta KD. And on the right, we have, I guess I could factor out the Ks. 1 plus theta KD. And finally, we have an equation for S that, you know, a little messy, but looks like maybe that's reasonable. Ks times 1 plus theta KD divided by theta mu max minus 1 minus theta KD. Okay, so we just solved a mass balance for a very particular situation, right? No recycle, first order stuff, and we have a growth of bacteria and a death of bacteria and a consumption of substrate. So we solved the mass balance that way. So when I highlight this equation, this is very specific to the no recycle case where we have a CSTR and all this stuff, right? In the past, we've done some derivations. We've found a mass balance for X, Y, or Z specific to a given condition, but we saw it several times, right? The mass balance for first order decay in a CSTR, you've seen several times. Pretty simple situation. This one's not so simple. This is quite particular to this case. I mean, any mass balance we solve is usually quite particular, but this one, just make sure you're not trying to use this. I think if I give you a question like this on the exam, I'm probably giving you this formula. So it's up to you to know that this formula is only for this condition, where there's no recycle. It's kind of like the lake example, right? And this is the solution to the mass balance on X, right? We did the mass balance on the bacteria concentration. Okay, so let me put in the numbers here, or rather look at when I previously put in the numbers. It turns out to be the same number as the problem example, which is super clever. This is 6.9 milligrams BOD per liter. Okay, so the answer there is that for this problem that was pretty involved. Okay, does that make sense? Did you get to the point where the algebra was annoying? Yeah? Did you get stuck there? Yeah. I don't blame you for that. Okay, but the nice thing is if you got to that point where you're recognizing this is annoying algebra, well, you kind of got the core concepts of the problem, right? And that's what I'm hoping for you to be able to see is like, given a little direction, you're able to put in, you know, the rate equations into this mass balance and go there. Okay, so next time we'll come back and start there to solve B and C. We'll be a little simpler from there, a little more algebra again on C, but we'll get it. All right, see you on Thursday.